Hey guys, we are back. This time we're going to start processing the Wikipedia data. The last video was pretty introductory. I mean, all we did was set up Ubuntu to torrent stuff, and then we downloaded Wikipedia and took a brief look at the file. In this case, here's the file, and we ran this bzip2-dc to compress to standard out, or sorry, decompress to standard out, and then we give it the file name. Pipe into less means pipe is just like feed data from one stage to the next, and so less consumed the data that bzip2 produced. And as a result, we saw this on the screen, and we could page around and kind of explore it without committing to decompressing the whole thing to disk. And just to reiterate the technical constraints we have, Wikipedia is a 16 gigabyte compressed file. Uncompressed, it's much larger. I'm assuming in the neighborhood of 100 or 150 gigabytes. We have an 80 gig disk and we have 2 gigs of memory. So everything we do is going to have to be pretty careful about space one way or another. And when we started off on this, the goal was to do a word count inside Wikipedia. So we want to find all these text tags, grab the stuff inside them. So in this case, we're looking at pound redirect all the way down to there, and then grab the words from this, collect those up and count them up by word. This is a great opportunity to talk about how we go about doing that. I'm going to page over out of our VM just so we can talk about design. Okay. Let's get ourselves a text editor and we can talk about this. All right. Buffers, next, okay. So we have our data, right? And it looks like, well, okay, so the first thing we're going to do is extract text up to not text, or up to end text. And once we have the contents there, we're going to emit, so like for each of one of those blocks, we're going to emit words, one per line. After that, we're going to take that entire stream and sort it. And finally, we are going to grab runs of words that are the same and collapse them down to just a count. This is an operation called uniq-c to do exactly this. And to show you an example of what I'm talking about, let me create a file, and we'll have some words right in here. So let's say foo, bar, biff, foo, baz, biff. So here we have foo occurring twice and biff occurring twice, and the other words occurring just once. So if we write that out to a file, then what we can do is sort the file, and that gives us the sorted list, and we see biff occurring twice and foo occurring twice. Pipe uniq-c. And now we have the counts prepended to the words. So runs of continuous words get compacted. Now the important thing here is we can't say, cat just shows you the file as it is. It doesn't sort or anything. So if we did cat file pipe uniq-c, we wouldn't see uniq-c collapse anything, because uniq is only looking for the same word on the next line, like groups of words together. The reason it does that is for memory usage. If it tried to find all occurrences of the word foo everywhere, it would have to remember that it had seen foo once and then load the whole rest of the file before committing to account for it. So obviously that would be inefficient, and uniq is only looking at words that are grouped together. So the key here is sort, right? Sort is going to be the big thing that makes or breaks this process. Luckily for us on Linux, sort is really well engineered, and it's in fact optimized for exactly this use case. So all we need to do is write this extraction and then emit words one per line process. And to do that, I'm going to use Perl. Not for any particular reason other than that Perl is really good for this type of job. Do we have Vim, the text editor? Oh, we don't. So let's install it. You'll notice here it says sudo apt install, not apt get. Apt is basically just a synonym. So let's do this. Sure, let's install all that. There are different text editors that you can use. I'm most familiar with Vim. I've been using it for about 15 years, I suppose. You should not start with Vim. Probably, like if you're wanting something more comfortable, I would recommend Nano. In fact, I'll use Nano here just for the sake of example. We probably already have it. Yeah, we do. Okay. Nano gives you like all the keyboard shortcuts. You know, it's helpful. This little caret X means Control X. You don't need to capitalize X. It's just Control X. Okay, so let's edit ourselves a Perl script that will do the thing we want. I'm going to write it out kind of longhand. There are shorter ways to do this, but let's do it this way. Wordify. Okay, so it's customary for Perl scripts to begin with what's called a shebang line. User bin env Perl. Use strict. Use warnings. That's a fairly common way to start a Perl file. I'm not really going to use this series to talk about learning Perl unless that's what people want. So I'll skim over a lot of this. Okay, while standard in. This basically will consume every line from standard in, and each line will be stored in a variable called $_. It's also the implicit variable. So really what we want to say is next, unless we have a start text up to end text. So next in Perl is just, it means skip over to the next iteration. So ignore the line unless it's within the range of lines that begin with a start text tag and then end with an end text tag. If we just did this and then we said print, I suspect what we would get is all of the text lines, but let's try it out. So we have bzip2-dc and wikipipe, or and wiki that, pipe Perl wordify, pipe less. Yeah, that's right. So we're getting the line beginning with text up until the end text tag, and then everything else, all that gibberish about page and the header and stuff is all gone, and that's exactly what we want. I guess the only other thing we need to do is just trim out the actual text tag. So we want to get rid of this chunk here and this chunk here, and that can be done with a search and replace. So let's do that. S text up to, but not include. Yeah, so any non-wicket characters up to the wicket, we get rid of those, and then we get rid of that too. This S regex replacement is what this is. So search for this and then replace it with nothing is what we've done. So that will now get rid of all the text tags, and we just have the words. Awesome. We're actually almost done with this part of it. So the only other thing we need now is to split it into words. And it turns out that that's all we need to say. All we want is continuous runs of words. And when you write this regular expression with a G quantifier on it, G modifier, G is global search. And so in an array context, it'll just give you all the matches of whatever you're looking for. So what we're really saying is print the thing for each time this regex matches the line. And actually, I'm not quite right on that. We need to say, we need to add a new line to it. Otherwise it'll all jumble together. So at this point, we'll actually get one per line, and I think we're in good shape. There we go. Look at that. So this is a stream of words, and it's just coming in incrementally as we decompress more of Wikipedia, feed it through our processor, and then the terminal, or really less, reads more stuff from it, which is pretty great. So now we're going to need to sort that. So the ultimate pipeline is going to look like this. Okay, but with a few modifications. We can't quite run this because sort is going to be a problem for us. And in order to imagine why that's the case, let's talk a little bit about how sorting usually works. In software engineering, a sort, you can imagine like a merge sort or a quick sort or whatever. Everything's in memory. And in Unix land, that's not really true. This sort utility here is not built for memory data sets. It's built to read stuff from standard input and then sort batches of lines and then ultimately print out the entire thing sorted. But the great thing about this is that it's designed for a memory constrained environment. So what it will do is it'll write temp files out when they get to a certain size, and then sort those individually, and then start merging them. So really it swaps things out to disk, but more efficiently than it would if you like use a giant page file. That's all great. The only problem is, as I mentioned before, we actually don't have enough disk space to store the uncompressed version of Wikipedia. This is where sort really comes in handy. Let's view the manual page for sort. Man is just manual. It shows you reference for a given command. So this sort is usually, most of it is specified by a common API called, well, it's POSIX compliance really, which means that it's going to be the same in most cases between Linux and like Mac OS X and all that. However, there are a few non-standard options. One of them is compress program. Now, this lets you specify which program you want to use to compress each temporary file as it's written to disk. And what that means is that you will never, potentially, write decompressed data to disk at all. That's really useful for us here because we need to make sure that we don't fill up our disk. So we would say this, compress program equals gzip. I will talk later about which compression programs make sense in which situations. For now, I'll just say that gzip is a really good general purpose compressor. If you don't have a strong opinion about how data is compressed, go with gzip by default. For now anyway, because right now it gives you a really good balance between speed and compression ratio. I say right now because as I'm making this video, there's a new thing from Facebook called zlib, or zstd, and it's actually really promising. It gives you good decompression speeds and potentially very high compression ratios. I haven't benchmarked it against gzip, so I'm reluctant to recommend it just yet. And gzip is already installed everywhere. However, in the future, zstandard might be the right way to go. Pipe uniq-c. Okay, now if we ran this, we would see nothing. Let's actually do it. That's it. It's running. We don't see anything. Ideally speaking, we have some way of monitoring what's going on, and there are a few ways we can do this. So Control-Shift-T to open a new tab in your terminal. Let's run some system monitoring software. So here's the original tab where that's going. This would take hours, by the way. This is not a fast command to run. So let's talk about how you monitor an Ubuntu Linux system, or just Linux in general for that matter. So first off, there's the classic top command. Top tells you what is using CPU. As is kind of predictable, you see sort consuming a lot because it's doing the bulk of the work here. bzip2 is also consuming a lot. This means that bzip2 is not a fast decompressor. Normally speaking, your decompression thing, unless your pipeline is really fast and ours is not, your decompressor is not likely to be the bottleneck in this, but like, you know, it's using a fifth of the CPU. It turns out bzip2 is known to be slow. It's not a fast compression algorithm. This is one of the reasons you wouldn't default to using it, although it's not terrible in this case. And yeah, as predicted, sort is using a lot of CPU time. Let's go take a look at the disk space that sort is using. This will be in /temp. There we go, sort temp files. So these are, you can just inspect these, I suppose. Less that. Yep. So good news is this is compressed data. This is binary gzip data. Yeah, that header, this is not something most people would just know, but these 2 bytes indicate that it's gzip data. And so you could zcat that, or gzip-dc pipe less, if you wanted to see what that is. Yeah, it's a bunch of zeros. I guess 0 is a word, and it was sorted. Okay, but anyway, we can look at how much space we're using up here. These are actually not big files at all. These are pretty small. One of the reasons is that sort doesn't use a very large memory buffer by default. That's another configurable option that we're going to be changing in a moment. But first, before I get there, let's monitor CPU and memory and that kind of thing. Top gave us a view of this, but it wasn't great. For example, we have 75% user CPU usage, 19% system. This is basically program usage versus kernel usage is the way to read that. This memory display is not great. It doesn't show you much of what the real state of the system is. I recommend actually not even using top at all. There's a better tool out there, which we probably don't have, called htop. Yep, so sudo apt install htop. Oh, it's offering you snap here. I don't recommend using snap for the most part. Snap is an alternative packaging thing for Ubuntu only, or primarily. But it works differently from apt. It uses containers, and it's a whole thing. I'll get into why I would recommend against it for at some other point, and it does have its uses. But for like casual data science work like this, I would recommend sticking with apt. Okay, so here we go. This is a better and more useful display. So we have sort consuming CPU and so forth. That's all fine. In particular, we have this nice memory bar up here. And this green area is committed memory. This is like stuff that the system can't get rid of. Like the rest of this is optional stuff, buffers and I/O cache and stuff like that. So the system is at liberty to use the rest of this. When it gives you numbers up here, 1.07 gig out of a total of 1.94, that's committed memory usage, meaning that you can't, like, you only have 0.87 gigs of remaining memory left if you wanted to use more. And that's kind of a hard limit. So that's what that's telling you. Notice that we do have a swap file, but we're not using much of it. That's good. We don't want to be using swap file. So let me hit less than, which will kick open this menu to let you sort by different things. %CPU. Yep, still in sort. So before we let this run for too long, let's do a couple of things that will give us more insight into how it's performing. There's a great tool called PVPipe Viewer, and I highly recommend using it when you're doing data science work. What PV does is it shows you how fast data is moving through your pipeline. And I really like seeing that because it will just kind of put things into context for you. In fact, it'll also give you progress bars on the files if you use it like cat. So let's go ahead and kill this with Control-C. Okay, so to switch this to a PV pipeline, all we have to do is move this file back here and open it with PV instead of bzip2. Like this. So PV is looking at how fast bzip2 is consuming data from the file, and it knows how big the file is, and so what it's doing is giving us an ETA for the pipeline runtime. It's actually pretty useful that way. Now we need to do one more thing, of course, which is to change the sort memory usage. Right now it's allocating tiny little buffers and then writing them all to disk very quickly, and that's not really going to make anything go very fast. Sort gets better leverage if you use larger memory buffers. So let's man sort again and find out which option that is. I think it's buffer size or something. Where is that option? Oh, buffer size, there it is. Yeah, buffer size, -S. And let's go with, I don't know, 128 megabytes. That should help it a lot. There we go. And let's go ahead and go back over to an htop and make sure we're not running totally out of memory. Okay, cool. It seems to be pretty stable. Yeah, and so over here in htop, if we go to the sort process right here, we see the memory usage. The virtual is 144, resident is 130. That's kind of the operative figure here is resident. And then shared we don't care about. Yeah, that sounds completely reasonable to me. Okay, cool. So that's running. It's going to take quite a while to run, but that's the basics of the pipeline. Oh, actually, before I cut this video off, okay, technically we're done writing the pipeline. However, we have a major problem. It would be the worst thing in the world if we just let this run and then it finished, because what would happen is sort would output all of this data that it spent 8 hours processing, and then we would uniq-c it, and then it would go into the terminal and disappear forever, basically, because the terminal can't hold all this data. So let's kill this, and as the last step in this process, we're going to pipe it into gzip and then write it out to a file, which will be the word count.gz. And that is the entire data pipeline. So when this thing finishes in some amount of time, I may run it on a faster machine in the meantime just so we get results earlier. I will make the next video and talk a little bit about something else, I suppose. I don't know what yet. So I will see you then.